So we've obviously been talking about bonding in these last couple of chapters. Yesterday we talked about sort of geometries that obviously go with our Lewis structures. Um, remember that we basically talked about two types of names. One is sometimes referred to as electron geometry or electron pair geometry. That again describes basically sort of the arrangement of the electrons around the central atom. When we have it doesn't matter what type of electrons are there, bonding electrons, non-bonding electrons, sort of just how the actual electron pairs are arranged around the central atom. We also talked about the molecular geometry, which is also sometimes referred to as the shape of the overall molecule. And what we sort of saw was a couple of things. First off, we saw that if we pretty much have only one type of electrons present around the central atom, which say are bonding electrons, so pretty much all bonds there around the central atom, no non-bonding electron, no dots really when you sort of draw your Lewis structures. So if you have a situation where it's all the bonding electrons present, no dots, then both of those names, electron pair geometry name and the molecular geometry name, will be the same name. And that's because we're really dealing with electrons that are really tied to atoms. So both the electron pairs and the way they can sort of separate themselves from one another, and how the electrons and the bonds and the atoms themselves can separate from each other are essentially the same. So we end up with really the same geometries for both of those things because they're really all bonding pairs. Remember, the basis of all this is the idea that obviously we have electrons near electrons, which really don't like to be near each other. So they do try to sort of get away from one another as best as they can. They're obviously locked into bonds, so they can't fully escape one another, but they will sort of, move a little bit and kind of spread out as best as they can to try to keep enough space between them and some other electrons. And we really start to see a difference in terms of those two names between the electron pair geometry name and the molecular geometry name when we start introducing non-bonding electrons into the mix. So when we start entering around that central atom, some non-bonding electrons, what that does is it creates, as we saw, basically three types of electron interactions. We could have bonding electrons near bonding electrons, which is basically lines near lines, basically in your Lewis structure. That's pretty reasonable in terms of the repulsion forces that they feel. The next sort of worst situation is where we get sort of non-bonding electrons near bonding electrons, again, in terms of Lewis structures, kind of dots near lines. Those don't really like to be near each other. So they're going to try to spread out a little bit further. And sort of the worst in terms of repulsion forces is when we get non-bonding electrons near non-bonding electrons, like, for example, what we saw with water. In that situation, those electrons definitely want to get further away from each other. They're able to do that because we have these non-bonding electrons and we don't have those electrons sort of locked into another atom on the other side. So there's not that extra sort of bond we have and that atom there kind of locking things in. So what it does is it does give sort of the overall molecule a little bit more room for movement. And what we end up seeing is that the molecular geometry name is actually the one that ends up changing in that particular case. So when we start introducing non-bonding electrons to the mix, it is the molecular geometry name that will differ. So for example, up on the screen there, we can see octahedral. Octahedral, that is all bonding electrons here involved. And again, both of the names are the same. We see no dots around the central atom. So all of these bonding electrons are pretty much attached to atoms, kind of keeping the distances between the atoms, allows it basically to get the same sort of geometry. By just removing one of those guys here, for example, and we get those non-bonding electrons in, what it's able to do is give a little bit more space because there's not this extra atom sitting there. So it gives it a little bit more space for these guys to kind of spread out a little bit. And we do start to get, as you can see here, different names between the electron pair geometry, which is over here on the left, and the molecular geometry, which is on the right. Same thing that happens as well. We get a couple of extra spaces there, a little bit more room for movement. Also, these non-bonding electron pairs are going to try to spread out as best as they can. And again, we end up with some different names, and also slightly different bond angles usually will occur in most cases because of that slight change that occurs between the sort of the presence of those atoms and the presence of obviously no atoms there gives it a little bit more room. Any questions on sort of that geometry stuff that we talked about? You are responsible, as we talked about, for both of those names, being able to correctly identify them. And as we talked about up to this point, you're sort of responsible for being able to draw the Lewis structure, a correct Lewis structure, obviously calculate things like formal charge, and obviously apply geometry to it, both to electron pair geometry and molecular geometry. One last thing, though, before we sort of move a little bit away from sort of geometry, is, sometimes, as we talked about, there is more than one central atom present. We don't come across it a lot in this class per se, but it does pop up. A lot of times people like to give organic sort of examples. So if we draw something like this, and this particular guy here, which is methanol, and it's an organic guy, we actually have two different central atoms. We have basically the carbon and we have the oxygen. These are both really central atoms. And you could apply this sort of geometry here to each of these guys individually. So these are both really center atoms. So basically what you would do in sort of a situation like this, if you have multiple sort of central atoms, is you apply the geometry basically to each one individually. So for example, if we started with the carbon here, what we would essentially do is sort of think about, like, can't really do it here on the screen, but normally what we would do is kind of just put our hand over this part of it, kind of just put your hand over that part of it and just look at the carbon like you normally would, like it was there by itself. The important part, though, is if we were to count this up, is we have one electron pair here, we would have one electron pair here, we would have one electron pair here. And even though technically we're kind of putting our hand over this part of the molecule, we would also count this as an electron pair as well. So you would still count that one on that side. And that would tell us it has 4 electron pairs. And we would do the same thing in terms of bonds. It would have 1 bond, 2 bonds, 3 bonds. And again, we would also count this guy as a bond, and that would be 4 bonds. And what that would tell us for the carbon here is that the electron pair geometry would be tetrahedral. Oops. And the molecular geometry would also be tetrahedral in this case. Again, just solely looking at the carbon, there's no non-bonding electrons present, obviously. So we see no dots, and that's, again, as we just talked about, why we see both of these names, again, being the same. Once we would do that, essentially what we would do, and I'll just redraw it this way here, is basically we would take sort of the same approach as we did for the carbon for the oxygen. So essentially what we would do is, and again, normally just kind of put your hand over it, but basically we would now kind of put our hand over the other side and look at just the oxygen in this case. And if we look at the oxygen in this case, again, we would count up our electron pairs. And if we were going to do our electron pairs for the oxygen, 1 electron pair, 2 electron pairs, 3 electron pairs. And again, much like what we did with the carbon, even though we would kind of be putting our hand over that side, we would still count this guy going in there, obviously, as an electron pair. So this has now 4 electron pairs. And again, in terms of bonds, we would have 1 bond there. Again, we would also count the bond going into the carbon, and that would be 2 bonds. So for the actual oxygen here, the electron pair geometry would again still be tetrahedral. But now, because there's only two bonds, we have those non-bonding electrons, the molecular geometry would be bent or V-shaped. And actually, if you sort of were to build a model of methanol, it would kind of look like that. You would have your sort of tetrahedral sort of arrangement there with the carbon, and then you get this kind of bent or V-shaped sort of guy coming down here where we have the OH group sort of happening. So it is possible, obviously, as we've seen here, and we talked a little bit about previously, you know, that you can have multiple central atoms, and you can definitely apply sort of the geometry to each atom separately. Again, basically, you just kind of put your hand over one half of it, and then, you know, do the geometry, and then go put your hand over the other half, do the geometry, and so forth. And again, if you had 3 or 4 central atoms, you would just kind of continue that pattern. If they happen to be the same elements, which sometimes happens, especially if you're given some type of organic guy, you know, you have multiple carbons, for example, you know, something like this. A lot of times what people will do is just kind of number the carbons, like this is carbon 1, this is carbon 2, and go carbon 1 has this geometry, carbon 2 has this geometry, carbon 3 would have this geometry here. So, you know, you could have multiple guys, and again, we would just kind of continue to put our hand over the rest of the molecules and then kind of do the geometry for each one. Just for purposes here, carbon 1 here would have 4 electron pairs and 4 bonds. The molecular geometry would be tetrahedral. The carbon number 2 would also end up being tetrahedral in terms of the molecular geometry. Carbon number 3, though, would have 1 electron pair, 2 electron pair, and 3 electron pairs, and only 3 bonds. So carbon 3 would actually have trigonal planar in terms of its molecular geometry. So, you know, if you have multiple of sort of the same element and you're doing geometry, a lot of times you number them and sort of give the geometries for that. Any questions on, again, geometries and how to apply this sort of thing here? Yeah, so we talked a little bit about it last time, and in terms of the question was, whoops, scribble there, about sort of bent and angular. And you can see here in this table, they do use bent, and it's very common. But for our purposes, for something like this, which is basically 3 electron pairs and 2 bonds, you probably should go with angular. And it is, again, as you can see in this table, people use bent. And like I said, I think when we're doing it, sometimes people even use, kind of put them together, bent, angular. And there really is sort of a difference, as we talked about, between that bent and like really this guy down here, which is bent or V-shaped. And the difference really is sort of in the bond angle between 120 and 109.5. So when we talk about kind of the angular, the 3 electron pairs and 2 bonds, we're kind of looking at a bond angle closer to 120, a little less than 120, obviously, but a little bit closer to that 120-ish sort of thing. While when we talk about sort of 4 electron pairs and 2 bonds, because of those extra non-bonding electrons that are present here, they are going to try to get away from each other a lot further, and we're going to get more sort of steeper bond angle there of 109.5. So for our purposes, I would go with angular for this guy right here, probably, you know, but I'll be honest with you, people definitely use bent for that as well. But there is sort of, like I said, sort of a difference between the bond angles that go with those two, and sort of what you're talking about in terms of that. But it is very common people will use bent for angular. So yeah, they're kind of the same. Yeah, so in terms of diatomic molecules, so usually when we talk about sort of electron geometry, which is the other question here, we usually see the electron geometry kind of for our three or more sort of atoms involved in the molecule. Like all these here in these examples, obviously you have three or more atoms. And what that does is when you have three or more atoms, it gives you sort of a central atom, right? And the electron pair geometry sort of describes the central atom that's going on there. When we're dealing with something that's sort of diatomic, there's really only obviously two atoms, and there's not really a sort of central atom that happens in that case. And so really, we just sort of focus more on the molecular geometry, which would be linear. And that's really more of the molecular geometry. You could technically, I guess, put it for the electron pair geometry, but usually the electron geometry kind of is for the central atom. And again, in a situation where you only have two, there's really technically not a central atom that's happening in that case. So if you want I know we split it off, and you might have some on those charts and stuff like that. So, if you want to put linear for both, it's okay. But usually, we're talking more about the molecular geometry as sort of a diatomic sort of situation. And it's because it really does lack a central atom. And, so usually we see the electron geometry as around the central atom. And obviously in that sort of two atom situation, there is not a central atom. Other questions on bonding? Okay, so we talked about this, which is sometimes a valence model here with our sort of geometry and stuff like that. We're going to talk about another sort of model of bonding, and there's a few different types of models, sort of valence theory, which is sort of what we've been talking about. There's hybridization, which we're going to talk about here, and something referred to as molecular orbital theory. But we're going to talk about sort of hybrid orbitals now, and sort of hybridization, and sort of what occurs when we deal with hybridization. And hybridization is sort of a model that describes bonding in a slightly different way than what we might be thinking about it. When we talk about sort of the valence bond model, it describes covalent bonding as really an overlap of some orbitals here. So sort of what we've been talking about here in the last situation. And there, if we take our two sort of 1s orbitals for two hydrogens, when we put together something for H2, we get this region of overlapping. And the idea here is this is sort of the region where obviously the electrons would be shared between those different orbitals. And what keeps basically that bond together, right? So we got the electrons kind of shared here between them. Electrons kind of attracted to this nucleus, attracted to this nucleus as well. And again, that's what's going to kind of keep everybody sort of locked into place. Now, the idea of hybridization is this idea of, well, this might be okay, obviously, when we are putting together, say, a couple of s orbitals like we have in this particular picture here. They're both probably the same shape. They're both the same sort of energy. But we do run into a little bit of a situation if you think about just theoretically how these guys would come together if perhaps we took a p orbital and an s orbital and try to mix those together in terms of a bond. Remember, an s orbital kind of looks like this. A p orbital is sort of a figure 8 sort of guy happening. There are also usually differences in terms of energy. So when these guys would try to come together to perhaps overlap and share electrons, here we're trying to mix together things that are sort of different shapes, theoretical sort of shapes, also different energy. It doesn't make for good overlapping happening and those orbitals coming together in a very good way. It also doesn't necessarily adequately describe maybe some of the bond angles that we see with some of these molecules that we just talked about there with our Vesper sort of theory. So the idea of hybrid orbitals basically comes about, and this idea or this sort of model of bonding is basically we take the atomic orbitals of proper energy and orientation in the same atom, and they get hybridized. And when we talk about atomic orbitals, a reminder of what we are talking about here are basically the orbitals that we've dealt with since electron configuration: S's, P's, D's, F's. So these are our atomic orbitals. So what we end up trying to do here sort of in this model is we take these atomic orbitals, which are S's, P's, and whatever it may be there. They're obviously different shapes. They're at different energy levels. And we sort of mix them together. And the result of mixing them together is we create basically orbitals that have the same shape and the same energy. So again, instead of trying to mix together sort of a p orbital, which is sort of your figure 8 sort of shape and a little bit different in terms of energy, with something that's like an s orbital, it's a spherical sort of shape and lower in energy, we kind of take them together, mix them together, and we end up creating these hybrid orbitals that basically are kind of the same shape. I'll draw a really bad shot of it, kind of the same shape, and also kind of the same energy level. And that's going to allow these guys to perhaps come together with a lot better overlap than if we try to take, these two guys and stick them together and stuff like that. Now, the total number of hybrid orbitals that we form is equal to the number of atomic orbitals that are hybridized. So what does that mean? Well, it means sort of like this. If we, for example, take a s orbital like this and a p orbital, we just take one of these guys, one of each of these guys, and we put them together, and this goes through hybridization. It would create two sp hybrid orbitals. So what does the S and P mean? Well, it means pretty much that. You took an s orbital, you took a p orbital, and you put them together. That is two atomic orbitals that, once it goes through hybridization, will create two hybrid orbitals. So the number of hybrid orbitals that we get, which again will end up being the exact same sort of shape, be sort of the exact same energy level, basically equals the number of hybrid orbitals that we basically take together and hybridize. So let's talk about sort of the first type of hybrid orbital that we could come across, or situation. And the first hybrid orbital is one that is pretty much what I just drew there, which is described as a sp hybrid orbital. It's the simplest sort of hybridization that can occur. And basically, let's think about sort of how we get this. So hybridization gets confusing for a lot of people in terms of how do I sort of choose what is the hybridization that's going to happen there. So this way is sometimes the easiest thing to think about. If you think about sort of like electron configuration and stuff like that, s orbitals, there's really just one line, right? P orbitals, there's 3 p orbitals, d orbitals, there's 5 d orbitals, and so forth. So when we talk about hybridization here in sp hybridization, basically what we're saying is we're going to take one of these s orbitals and one of these p orbitals, basically, and we're going to hybridize it. So we've now taken two of these atomic orbitals that will generate us two sp hybrid orbitals that will come into play. Each of these hybrid orbitals will also have an electron available for a bond. And here's sort of the hybridization process. Again, you can kind of see this circle here is your s orbital. There's our p orbital on the particular axis there, that kind of figure 8 sort of guy in blue. And when they come together, kind of like a little kidney shaped guys, they make kind of these two hybrid orbitals that are sort of kidney shaped, again, equal in terms of energy. And hybridization really does sort of follow the electron pair geometry that we've been talking about. So the hybridization does follow that electron pair geometry. So it ends up being 180 degrees apart. And if you remember, what was 180 degrees apart in terms of electron pair geometry when we had two electron pairs? When we had two electron pairs, that gave us that linear electron pair geometry that's 180 degrees apart. And that's exactly what we have going on here when we talk about sp hybridization, is we get the linear electron pair geometry. So what happens in this case, if we look at an example, for example, BeF2, and BeF2 is our boron fluoride here. And if we kind of look at the electron configuration here, and what we're looking at here is actually the Be atom in terms of its like orbital sort of diagram here. So this is Be, and remember Be is basically number 4 on the periodic table. So Be is 4, which means electron configuration 1s2, 2s2. Remember, we're talking about bonding here. So we're talking about its valence electrons, which is group number 2. And we're talking about these 2 valence electrons. So that's what the electrons that we see right here. And what we're talking about here are these 2s electrons. It obviously has the 1s electrons lower in energy, but not involved in bonding because, right, this is the core electrons here. Right? And this is our valence electrons. Now, when we go through this sort of process of hybridization, what ends up happening is in this process of hybridization, the electron or one electron in the lower energy level ends up being sort of promoted to a higher energy level. Because right now at the start, there's really no electrons in the p orbitals of beryllium. So what ends up happening in this process of hybridization is this electron down here gains enough energy and actually gets promoted up into the p orbital. And when it does, we now get one electron up in the p orbital and one electron in the s orbital. And that's when hybridization is going to occur. Basically, the s orbital and the p orbital here are going to go through hybridization. And when it does that, again, as we've been talking about here, we are using one atomic orbital, two atomic orbitals. So we have hybridized two atomic orbitals, which means we're going to create two hybrid orbitals here in the beryllium. Again, both of these guys would be of the same sort of shape. They also would be the same sort of energy. And we will also have two unhybridized p orbitals. So these guys over here are unhybridized. They're just regular old run-of-the-mill sort of p orbitals, right? Figure eights. These are two sort of hybrid orbitals. I'll just draw them like this, bad drawing, but basically same shape, same energy, two hybrid orbitals. Each of these guys containing one electron, which is going to allow it to do some bonding. We also see that one of the processes of hybridization as well is these hybrid orbitals also end up a little bit lower in energy from where they started from. And that also is really good, right? Because things want to be in sort of lower energy. So this idea of hybridization brings everybody kind of down a little bit in terms of energy, also creating these sort of guys. So what does this really mean when we look at this? So if we drew the Lewis structure for this guy here, what is sort of those hybrid orbitals sort of mean and what's happening? Well, what's happening is this hybrid orbital here, and again, this is beryllium. This guy has one electron, which let's call this bond number 1 and bond number 2 happening here. This one electron allows beryllium then to bind with a fluorine and do some overlapping there with a fluorine. And this guy allows the beryllium to also do a bond with the other fluorine that's present, which would represent sort of this second bond. Now, what we have in terms of bonding that's occurring here is we have basically this guy being sp hybridized. Any questions on that there? So if we look at this, again, it has basically two electron pairs. So if we were to go to this central atom and we were basically going to count up electron pairs like we did with molecular geometry and all that stuff that we did before, we would go here and go one electron pair, two electron pairs. This again is counted like we would do geometry like we did the other day. And this is obviously an incomplete octet, right? So this is not meeting the octet rule in this case. So how would you, just looking at the Lewis structure, know the hybridization? Again, the simplest way to do it is just to draw this and really count. And what you would do is go, okay, well, I have two electron pairs starting at the s, 1 and 2. I've used an s and a p orbital, which means this is sp hybridized. So that's like the simplest way. You can always get the correct sort of hybridization from a Lewis structure, is just to do exactly what I just did right there. Any questions on that particular one there? Okay. The next sort of hybridization that's going to occur is one where we're going to take basically one s orbital and a couple of p orbitals. That's going to happen. This is going to give us a hybridization known as Sp2 hybridization. And again, if you kind of look at the little diagram here on the left, this is sort of before it goes through hybridization. Again, you can kind of see the red guy there. The red circle is our s orbital. Remember, there's three different types of p orbitals, each on a different sort of axis, x, y, and z. And that's why we see kind of one figure 8 coming through here and another figure 8 kind of going from the back to the front happening there. And those are the two p orbitals basically happening here. And s orbital. So basically what we're taking is one s orbital and two p orbitals are going to hybridize. It's going to give us, again, these kind of kidney shaped sort of structures. We're going to get three of these sort of kidney shaped structures that ends up being basically in a triangle sort of form, 120 degrees away from each other. So if you think about, again, our electron pair geometry that we talked about, when we have three electron pairs, that is our trigonal planar geometry for our electron pair geometry. And trigonal planar, again, goes with the Sp2 hybridization that's basically occurring. You can literally count the numbers. There's an S, or letters, an S and two Ps, S3. So one S and two Ps is three electron pairs, trigonal planar in terms of its electron pair geometry and what the hybridization would be. So let's take a look at an example of this type of hybridization that's happening, and one that we sort of talked about, I think, with geometry, and that's going to be our BF3. BF3, again, going to be an incomplete octet happening here. So when we look at this original here, again, for reference, this is boron that we're looking at. So sort of the electron configuration there for boron. Partial, obviously, the 1s is not there. Again, boron being 5 would have 1s2, 2s2, 2p1. This, again, going to be the valence electrons that we see here in the picture, right? 1, 2, and 3 valence electrons. Again, our core electrons here not shown, but they are still there, obviously, on the bottom. Same sort of process is going to occur here that happened in the previous one. We're going to get this sort of promotion of an electron in the lower energy level it's going to come up. But as it comes up, just like electrons go into the atom, when we talked about sort of electron configuration and how they're filled, is they're not going to obviously go into this first box because there's already an electron there. So this electron, when it gets promoted, is going to go up into the orbital next to it. So again, we will still have the filling of those sort of guys like we normally would. This is going to then cause hybridization to occur, where we're going to take an s orbital, and in this case, two p orbitals that are going to come together. So we have now hybridized 1, 2, and 3 atomic orbitals. And that should give us, as we've been talking about, 3 identical hybrid orbitals that will hybridize. And those will give us 3 Sp2 hybrid orbitals. We basically have one unhybridized p orbital. There was just this guy, right? Nothing happened with this guy. So regular p orbital. By the way, right, this represents the px orbital, py orbital, and pz orbital, which means we actually know that this guy is actually the unhybridized pz orbital, right? This goes with our -1, 0, and +1 for our m sub l that we talked about in terms of our quantum numbers. Now, that is our unhybridized pz orbital. Doesn't have an electron in it, so it's not going to be involved anywhere that's going on here. But again, we now have these 3 hybrid orbitals available in boron basically to do some bonding. So again, if we sort of draw the Lewis structure here without all the dots on the fluorine, and we just focus in on our central atom here, again, basically we have a bond between boron and 1 fluorine, which could be this guy, for example. We have a bond between boron and another fluorine, which, could be this guy, for example. And we have a bond between boron and fluorine as well, and that is going to be here, right? Oops, fluorine happening in this case. So this allows, again, boron to end up with 3 hybrid orbitals, which each have 1 electron in there that it could then go and share in a bond with fluorine through some overlapping that's going to happen between a fluorine hybrid orbital, or fluorine, and the boron hybrid orbital. And again here, how would you determine the hybridization if you just started with the Lewis structure? Again, the easiest way to do it is to keep it very simple. Draw your little S, P, and D. And basically you would go to your Lewis structure, count up the electron pairs like we did. That also means that if we had a double bond or a triple bond, just like we did previously, it would count as only 1 electron pair and go 1 electron pair, 2 electron pairs, 3 electron pairs, and then go over here and go 1, 2, and 3. And you could basically just count up that I just used an S and 2 p orbitals, which would give me Sp2 hybridization basically occurring here with our boron in this particular case. Again, it is related to obviously 3 electron pairs, and that 3 electron pairs is that trigonal planar and that 120-degree sort of bond angle that's happening here. Question on that there? Then let's take a look at another common hybridization, which is Sp3 hybridization. And as you can probably imagine at this point from our conversation here, Sp3 basically means that we're taking 1 s orbital and 3 p orbitals and basically hybridizing them. You can kind of see it here. There's our s orbital, and hidden in here is all 3 of our p orbitals. Again, you can see the px, py, and pz sort of access that's probably happening here. And again, they're going to hybridize, and they're going to give us, because we're taking 1 s orbital and 3 p orbitals, going to give us 4 hybrid orbitals. And you can kind of see it here, 1, 2, 3, and 4. These guys are separated by, again, a very common bond angle of 109.5 degrees. So basically, if you think about how that ties to our electron pair geometry that we talked about, we have 4 electron pairs. Something with 4 electron pairs has an electron pair geometry, a tetrahedral, and a bond angle of 109.5. So this sp3 hybridization basically correlates to tetrahedral electron pair geometry. And again, we have basically our same process happening here. We're going to get those hybridizations to occur. And we're going to actually, in this case, generate 4 equal hybrid orbitals of the same shape, the same energy, again, going to allow some better overlapping to sort of occur. So if we take a look at an example of this would be CH4. So again, here, what we're looking at is carbon. And if we look at carbon, it is number 6. So 1s2, 2s2, 2p2. And here is carbon's 4 valence electrons. As you can see here, 4 arrows to represent those 4 valence electrons. Again, much like the other ones we looked at, they are still there, but our core electrons, again, are not shown here in this diagram as they're not involved in bonding. Excuse me. So what's going to happen here is, again, the same sort of promotion that we're going to get. We're going to get this kind of lower energy electron going to come up. Again, same idea here. We're already filled. So our normal sort of filling would then be, he would come up into here, right? As that is how they go, right? One at a time before they come back and start sort of filling up. Basically going to go into our PZ orbital there. We now have 1 electron in each of these atomic orbitals. In this case, all 4 of these guys are going to go through hybridization. Again, we basically have taken an s orbital and 3 p orbitals, and that's going to get us basically 4 equivalent hybrid orbitals, which are sp3 hybrid orbitals in our carbon. And again, if we look at our structure here for methane, what's going to happen is we basically have 4 bonds, right? We have a bond there, we got a bond there, got a bond there, and a bond there. Each of these bonds are between a carbon and a hydrogen. So all these guys here on the right are basically carbon with 1 electron available to make a bond. We would get a bond with a 1s orbital from hydrogen, another one to another hydrogen, another one to another hydrogen here, and another one to another hydrogen here. Again, we would get this sort of overlapping that's occurring, representing basically our 4 bonds that we see here, again, in methane in this particular case. By the way, since we have hydrogen here, hydrogen really will not go through hybridization. It's one of the only elements that really will not go through hybridization because it only has 1 electron. So you kind of need more than 1 electron so you can get that promotion of the electron like we see here on the left of that electron to go up. So hydrogen will not basically go through hybridization. Everybody else can go through hybridization, but hydrogen really will not because it really only contains 1 electron. So what we know here is we actually end up, again, if we wanted to use our Lewis structure by itself to figure out what is the hybridization of it, again, simplest way that you could do it, you'll always get it right in this case. We would go to our Lewis structure, we would count it just like we did geometry before, 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. You would start here at the S, 1, 2, 3, and 4, and basically count up what you just did there. And in that case, obviously an S and 3 Ps tells us this is an sp3 hybridized carbon that's happening in this particular case because of it. we could actually get very specific here. And because we know hydrogen doesn't go through hybridization, we could say that this bond, for example, right here, is a bond between a carbon that is sp3 and a hydrogen that is a 1s orbital. So that is the sort of overlapping that's happening there between it. Hydrogen supplying obviously an electron. The carbon, one of the carbon sp3 guys supplying an electron. Again, that overlapping of those two orbitals is what's going to make that bond that we see. Question on that right there. Okay. So what happens though in, say, a situation like, let's talk about maybe here. Let's take a look at maybe something like NH3, for example. Let's take a look at NH3, which we also talked about. So what is happening here with NH3 in this particular case? Well, we're going to look at the central atom here, which is nitrogen, and we're going to look at the electron configuration for nitrogen. Nitrogen is 7, which is 1s2, 2s2, and 2p3. It has its 5 valence electrons basically here, right? So if we draw the Lewis structure for NH3, which we saw earlier, it looks something like this. And if we wanted to figure out the hybridization of our nitrogen in this particular case, again, the simplest way to do it is what I've been doing here. We would go to our central atom, which is our nitrogen. We would count up the electron pairs just like we did geometry. So 1 electron pair, 2 electron pairs, 3 electron pairs. And just like what we did with geometry, these dots count, right? So it doesn't matter if they're lines or dots. We count up the total number of electron pairs. Again, as we talked about, we would treat our double bonds and triple bonds like single electron pairs as well. Now, if we come over here, this is 1, 2, 3, and 4 electron pairs. So what this tells us is the hybridization on this nitrogen is an S and 3 Ps, which means this is going to hybridize as an Sp3 hybridization. So that is really as fast and as easy as you could identify the hybridization, just like I just did there. You don't have to draw any lines or arrows or anything like that. You could really just take your Lewis structure and do exactly what I just did there. And you could basically identify the hybridization right off of that. So what is happening in this particular case? So let's talk about sort of what we see here, because it's a little bit different than what we've been talking about. Up until this point, we've been talking about pretty much things that have bonds, right? So they're all bonds, but we do have some non-bonding electrons. So how does this sort of work in this particular case? Well, if we focus in on nitrogen, which is our central atom, again, we have our 2s, and we obviously have our 2p happening here. And to start with, we have our, we got our 5 valence electrons happening there. So 2, 3, 4, and 5. So what's going to happen in this particular case is we are going to get that promotion like we've been talking about. And what that means is this lower electron is going to go up. Now we run into a situation here that obviously all 3 of these p orbitals already have electrons. So just like what we do when we are dealing with electron configuration, we put them in one at a time. And at that point, the next electron that would come in, kind of the 4th one in this case, would go back to the first one in the opposite direction. So what would happen is this guy would actually end up over here in our px orbital, really. And what's going to happen is it's going to then be promoted up to here. And our 2p and our QS in our nitrogen. We would have one there. We would have one there, one there, one there. And now when that electron comes up, we would also have that one going down, just like we would kind of do electron configuration. Again, this being our PX, PY, and PZ. We are then going to get all of these guys to go through hybridization, as we have identified this as being Sp3 hybridized, an s orbital and 3 p orbitals. As it goes through the hybridization process here, we will then end up with 4 equivalent Sp3 hybrid orbitals in this case. Now, in terms of electrons, what has happened? Well, we have this, we have this, and we have this basically here. Now, when we look at these sort of bonds that are happening here, we could basically figure out, well, for example, we'll call that bond number 1. It's got to go with and again, this is nitrogen. It's got to go with a nitrogen that has only 1 electron, right, to go to hydrogen so it could share electrons to make a bond. This guy would also has to go with the guy that has only 1 electron. And our third sort of bond there would be here. And that accounts for basically the 3 bonds that we see in NH3. It's basically a bond between an Sp3 hybrid orbital and a 1s orbital for each of the hydrogen. But if we look at the nitrogen, there's these lone pairs, which implies 2 electrons. So what represents that? Well, those lone pairs are represented right there, right? Those are 2 electrons in there. It can't make a bond. There's too many electrons already. And that represents the lone pairs are the non-bonding electrons on the nitrogen in that particular case. So this hybridization sort of model, in addition to sort of adequately describing what is happening in terms of the bonds in a particular sort of situation, it also, as you can see here, basically accounts for the non-bonding electrons that we see occur here on the nitrogen in this particular case. Any questions on that there? So let's talk a little bit about sort of these bonds and sort of how we describe some of these bonds and these things that are happening here. Now, we describe these bonds and the overlapping that's occurring a couple different ways. One way that we sort of account for it is what is referred to as sigma bonds, and we'll talk about what that is in just a second. But as we just saw there with our NH3, and it also happens with our water as well, we get this sort of non-bonding electrons basically accounted for when we look at oxygen. We can have basically these hybrid orbitals having non-bonding electrons, which won't participate in bonds. So for example, here, actually, if we take a look at it real quick, take a look. So if we look at, we look at water, and I'll actually do it right about here. We look at water and we look at its Lewis structure. Again, we can basically kind of apply the same sort of thing here. Erase some of this, give it a little bit of room to draw, I think. There we go, go this way. So if we look at it, we want to apply hybridization to this guy. We would do the same thing. This is going to be 1 electron pair, 2 electron pairs, 3 electron pairs, and actually 4 electron pairs. So again, we would count it just like we were doing geometry. And if we were going to our guy here, we would have, again, our 1, 2, 3, and 4 electron pairs. So water, just like NH3 here, is going to end up as Sp3 hybridized, the oxygen that's there. And if we look at the oxygen, which is 8, oxygen, which is 8, 1s2, 2s2, 2p4, and this is going to be our 6 valence electrons that happens for our oxygen. So again, if we draw our just valence electrons there for the oxygen, that being our 2s, and then obviously our 2p, which would have 4, 1, 2, 3, and 4 to begin with. We again going to get that promotion that's going to occur. The next electron would end up over here in our py orbital, and that would get us and again we started like this, and that electron that came from the bottom would end up there. We're going to hybridize as sp3 as we talked about, which means all these guys are going to go through hybridization. And when it does, what I'll end up doing is I'll just steal over here, since I have it drawn there. We'll just call this now. We'll steal this and call this now oxygen in this case. Get rid of these guys. There you go. And what happens with our oxygen in this case is we would obviously have this situation happening. And obviously in this case, if we think about water and the bonds that are present, we have one bond which can happen here between this oxygen and the hydrogen, sp3 of the oxygen and a 1s orbital of the hydrogen. We have an actual bond happening here, which can happen, right? Because there's just one electron there. And the oxygen making our 2 bonds that we see. And now we also again see that our hybrid orbitals here account for our non-bonding electrons around this center atom there as well. Again, already filled to begin with, not available to make bonds. Our non-bonding electrons, they're accounted for in these 2 sort of hybrid orbitals there where they're filled. So again, the hybridization orbitals or the hybrid orbitals do account for both the bonding electrons that we see, the bonds that we see in these Lewis structures, and also the non-bonding electrons that we see in these Lewis structures as well. So sometimes people are a little confused on that in terms of, well, the non-bonding electrons, do I count those? Do I not count those? So again, the easiest way to think about it is you want to count the electrons around the atom that you're applying hybridization to, just like you normally would. Again, doesn't matter if they're dots, it doesn't matter if there are sort of lines, bonding or non-bonding electrons, you would count them the same. Any questions on that there? So that's what this is saying here. Again, the hybridization, it does account for our non-bonding electrons, and that's what we see with our different geometries that we talked about, right? You can have 4 electron pairs and 4 bonds. You could also have 4 electron pairs and 3 bonds, 4 electron pairs and 2 bonds, and with our non-bonding electrons. So again, this does apply, to those guys as well. Now, when bonds basically are formed in what is described as a head-to-head orbital overlap, it creates basically that electron density along the axis, and those are what are referred to as sort of sigma bonds. So when we talk about sigma bonds, not 100% correct what I'm probably going to say, but we could kind of think about it this way. You could kind of think of sigma bonds as like single bonds, if you will. Again, not 100% perhaps correct, basically analogy, but you could kind of think of them as single bonds are like when you go to draw a Lewis structure, right? If you were going to draw a Lewis structure, the first line that you would make would be kind of like a single bond, right? If you were going to make a double bond, the first line would be like the single bond. The next one would make it like a double bond. If you're going to draw a triple bond, first line would be kind of like the single bond, double bond, and then triple bond. So you could kind of think of sigma bonds in that sense, that they are sort of like the first line that you would draw. You know, if you were only going to draw a single bond, you would have one line, and that would be a sigma bond. If you're going to draw a double bond, first line would be like the single bond or the sigma bond. And if you draw a triple bond, again, the first line there would sort of be like it. And what it really means is when we talk about how these orbitals basically come together to share the electrons, is in a sigma bond situation, the overlapping happens in what is referred to as it says there, at head-to-head overlap, which basically means that these two orbitals, whatever shape they are, these two orbitals basically come right at each other. They just go dead on to each other. They're both on the same sort of axis and plane and geometry and three-dimensional space, and they basically just run right into each other. And obviously, as they run right into each other, it creates this area of overlapping that's occurring between them. And that is obviously where we expect basically the sharing of those electrons to occur, and the bond basically to occur basically there in that sort of area of overlap. Now, because of hybrid orbitals being basically the same shape and also the same energy and stuff like that, we get a much stronger bond occurring in the hybridization model because they're basically the same. They're basically the same shape in theory. There's same energy. When they run right into each other, you know, they match up really well, kind of like two circles, right? They match up really well. Again, as opposed to if you had like the circle and sort of the figure eight, if they run into each other, like where do I overlap and all that kind of stuff, you don't get as good of an overlap to sort of happen in this case. So for example, if we look at a couple of things that we just talked about, you know, what could we describe as sort of a sigma bond? Well, we could describe, you know, for example, methane that we just talked about. When we would look at this methane, again, we could look at it, and if we were just had the Lewis structure and that's all we had, we could simply, like we did earlier, there go 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs. Again, that's going to give us 1, 2, 3, 4 electron pairs. Again, Sp3 hybridization happening there. And basically this would be 1 sigma bond, 2 sigma bonds, 3 sigma bonds, and 4 sigma bonds that would occur basically between an Sp3 orbital and a 1s orbital in the hydrogen. And this would be in the carbon. And these guys basically would go straight at each other, again, given that area of overlap that's going to occur. And that would be considered, again, sigma bonds. So something like CH4 would contain 4 sigma bonds. And again, really the definition of sigma bonds is just that. It's basically those orbitals coming straight at each other, head to head, sort of overlapping that's occurring. Any questions on that? We're going to talk about what happens when they don't come necessarily, you know, kind of head to head. You get some different types of bonds that occur. Same thing if we looked at, obviously, here in our, here's our NH3, and I think I jumped the gun there and did it a little bit earlier, but again, this is going to give us our ability to make our sigma bonds here. This again, our nitrogen, and each of these right in our NH3, which looks like this. Again, as we did before, 1, 2, 3, 4 electron pairs, going to be Sp3 hybridized, the nitrogen, again, because of that, like we saw earlier. 1, 2, 3, 4. And again, each of these in the nitrogen going to make a sigma bond. So this would have 1 sigma bond, 2 sigma bonds, and 3 sigma bonds that are happening there. And that's a little bit different than what we see there with water. Water, again, would have, so if you looked at the oxygen, also going to be Sp3 hybridized. Difference though is we already have our non-bonding electrons, right? Going to allow only 2 sigma bonds basically to occur. Sigma bond 1 there and sigma bond 1 there between an sp3 of the oxygen and a 1s orbital of our hydrogen, and same thing with our NH3. It would be an sp3 of our sp3 of our nitrogen and a 1s orbital of our hydrogen. So sigma bonds, again, kind of to really simplify sort of what sigma bond is, other than, again, really it is that way that those orbitals overlap where they come right at each other, sort of head to head overlapping. But again, the simplification of it is you could kind of think of it really as sort of that first line that you draw, or the single bond that you draw will definitely be a sigma bond in most cases. But what happens then, though, if we do get to something that contains perhaps a double bond or a triple bond? What happens to sort of form those type of bonds that occur? So let's talk about sort of what happens in that case, and we'll get there here. So for example, when we have hybridization that involves a double bond or a triple bond, there's a number of things that are sort of occurring in the hybridization model to allow those sort of bonds basically to occur. And hang on real quick, where did that go? So one thing that sort of occurs when we do have multiple bonds is we do end up with some electrons that are available to basically make single bonds. On the central atom with multiple bonds, we can also have some lone pairs, and we could also have some shared electron pairs in the multiple bond. So the electron pairs that make up really our double bond and sort of our triple bond that occurs actually comes from those unhybridized p orbitals. So if you remember, for example, when we looked at sp hybridization, you basically have 2 unhybridized p orbitals, right? So if you think about sort of, a couple, for example, sp hybridization, what does that mean, right? So if we just go back to the sort of the basics here, it means that we're going to hybridize an s orbital and basically a p orbital. That leaves us, as we saw earlier, 2 unhybridized p orbitals. And these are, again, just regular run-of-the-mill figure 8 sort of p orbitals. And that's really where our sort of double bond, triple bond is going to come from. If we had sp2 hybridization, what does that mean? Well, same idea. We just very much simplify it here. That means we're taking an s and 2 p orbitals. That's going to leave us 1 unhybridized p orbital. By the way, that would be the pz orbital, py, and pz orbital up here. So what does that mean? Well, that is really where these double bonds and triple bonds are basically going to come from. So when we get, though, a double bond or a triple bond as a result of these unhybridized p orbitals, it creates a different type of bond than a sigma bond. It creates what is referred to as a pi bond. And double bond and triple bonds coming from these unhybridized p orbitals create what are referred to as pi bonds. And the difference between a pi bond and a sigma bond is actually how the overlapping occurs. So as we were just talking about, the sigma bond occurs from basically those 2 orbitals heading straight at each other, head to head, overlapping. That's basically occurring. What happens when we have sort of pi bonds, double bonds, or triple bonds is we actually have these unhybridized p orbitals that are there, very badly drawn. And they are the same shape. They're most likely going to be pretty close in the same energy, but the way they overlap is what is referred to as sideways overlap. And the overlapping of these unhybridized p orbitals kind of even looks like a double bond when you do it that way, right? Makes a what are referred to as sideways overlap. Kind of above and below, if you think about the plane of the bond sort of happening right about here in the middle, kind of above and below sort of the plane of the bond. And that accounts for what is referred to as a pi bond, this sideways overlap. Again, different than what we see with a sigma bond, where we get sort of head-to-head overlap. Again, they're basically heading right at each other. These guys, because of the sort of theoretical shape of it, this figure 8, they're able to sort of overlap above and below. Again, this area of the figure 8, right, is the highest probability of finding electrons, right, in this sort of areas. And that's why we get the overlapping to sort of occur in that particular case. And that would account for a pi bond. Now, what happens when we actually sort of do a single, double, or triple? Well, to very much simplify it, when we think about a single bond and we think about sort of drawing the Lewis structure, we basically draw a single bond with a line. So again, sort of the first line that you would draw in, say, your Lewis structure, if it ended up just being a single bond, is most likely going to be a sigma bond, which has head-to-head overlap. If you were going to draw a Lewis structure that involved a double bond, at some point you would draw the first line, which again would represent like a single bond, which would be a sigma bond. And then you would draw the second line, right, to make that double bond, maybe not that far away. And that would represent a pi bond. So within a double bond, when you draw a double bond, it contains basically two types of orbital overlaps. We have a sigma bond, which is the head-to-head overlap that occurs. And then we have these unhybridized p orbitals that are doing the sideways overlap to basically, if you want to think about it, create your second bond for your double bond. Now, a triple bond, if you were to sort of draw that in a Lewis structure, you would draw one line, then two lines, and then three lines, essentially. So you could kind of follow the same process here. First line would be our sigma bond. Second line would be our pi bond. And the third line would be another pi bond. You may be saying, well, how do I get two pi bonds? It actually occurs right about here. In this case, you will have not one unhybridized p orbital, but you will actually have two unhybridized p orbitals. So you'll have a set of unhybridized p orbitals that will do your sideways overlap. Remember, p orbitals, right, are along the x, y, and z sort of axis. So you would have another set, and I'll try to do it in a different color. Maybe it'll help, probably not, and I apologize for the bad drawing here. But we have another set of p orbitals on a different axis, which would also do some overlapping that's going to occur here. Maybe green wasn't the best choice there. And that would be our second pi bond. So you have these two sets of unhybridized p orbitals. Again, within a triple bond, basically three types of bonds sort of occurring. You have this sigma bond, which is the head-to-head overlap. You have one set of unhybridized p orbitals sideways overlapping to make like the second bond. And then you have another set of p orbitals that are unhybridized sideways overlapping to make your triple bond in that particular case. Any questions on that there? All right. So let's see here. So let's also talk, and we're going to do some examples of this in a second here, I think. Let's talk about as well, since we're talking about sort of double bonds, triple bonds, and single bonds. And we've talked now about a little bit about non-bonding electrons and bonding electrons and how hybridization sort of accounts for that. Let's talk about what happens when we get to sort of our expanded octets. So obviously we can do our expanded octets. Those are, again, our guys with more than 8 electrons around it. Hybridization really does sort of account for those guys as well. And let's see here. We end up getting into our d orbitals, right? And that's what basically allows those guys to go over 8 electrons. So if you remember when we talked about why sulfur to the right and left has the ability to kind of go above 8 electrons, is because they do have those d orbitals available to them. And they do correspond to our electron pair geometry that we talked about as well. So if you think about really the two sort of electron pair geometry that we talked about, we had our triangular bipyramidal, and that was with 5 electron pairs. And we also had our octahedral that also had 6 electron pairs basically involved. And the approach to sort of figuring out the hybridization for these expanded octets really would be the same sort of approach that we just did there. You would want to draw probably your correct Lewis structure. And once you draw your correct Lewis structure, again, you can just use this basic way of really counting off hybridization and go, all right, 5 electron pairs means 1, 2, 3, 4, and 5. So in this particular case, I've used an S, I've used 3 p orbitals, and now I used a d orbital, which is why it's an expanded octet. And something that would have 5 electron pairs, again, we would count these just like we did everything else. Double bonds, triple bonds would count as 1 electron pair. Would have sp3 dehybridization. So what does that mean? Again, if we count up all the letters, that's basically 1, 2, 3, 4, 5 atomic orbitals. So it should yield you 5 sp3d orbitals, which are available for either non-bonding electrons around the central atom or bonding, right? So either able to make sigma bonds or non-bonding electrons. And again, you know, the central atom would be what we'd be looking at here, and they would be able to make those bonds. Same thing here, if we got to our octahedral, which basically is 6 electron pairs, we would count off here just like we did before, and we pretty much will end up very similar. 1, 2, 3, 4, 5, and 6. And we can see we've taken a S, 3 Ps, and 2 Ds in this case. And it would hybridize something with 6 electron pairs. Again, would hybridize an sp3d2 hybridization. And it would end up with obviously 1, 2, 3, 4, 5, 6 sp3d2 hybrid orbitals, again, each being the same shape, each being the same energy. And within those, you could have non-bonding electrons, you could have bonding sort of electrons occurring. So the take-home message in terms of hybridization, we're going to look at, you know, some more examples here in just a bit, but it really is tied to the electron pair geometry. So it is tied to linear, trigonal planar, tetrahedral, triangular bipyramidal, and octahedral. So the electron pair geometry that we talked to is basically how the hybridization is tied to, and you definitely would just need to count up the electron pairs and basically apply the hybridization. That probably the easiest way to do it is obviously either you're given the Lewis structure, draw the Lewis structure, and just like you were doing geometry, count those electron pairs, and basically you could literally count off the hybridization, just like I've been doing here. Any questions on that there? Okay, so I want to do some more examples of this. So I think what we're going to do is we're going to lay it up here for now. We'll do lab and we're going to continue lecturing on this, and we'll get into polarity and stuff like that, so that then you can complete, hopefully, study assignment B, which is the last couple of things that we were talking about. So we're going to do a little bit more lecturing, I think, just to wrap up these couple of topics here in terms of bonding, and that should hopefully put us on track. So we'll stop right now, and I'll see everybody about